And today it's my pleasure to introduce Rosalba Perna as our top colloquium speaker. Rosalba started her studies in Italy at the University of Salerno, but that's not where I met her. We met in the US, where she moved for her Ph.D. in Harvard, and then you remained in Harvard as a Harvard Junior Fellow. Then you went to Princeton for a Spitzer Fellowship. I have notes, but I'm not looking at them. And then afterwards, she moved to Boulder to become a professor, and now she's back in the Northeast at Stony Brook, and we met at CCA. Rosalba is a very broad theorist. She has worked on all fields from planetary to cosmology, and today we're going to be kind of in the middle of those fields for this talk. And yeah, I'm not going to steal any more time.
First of all, thank you very much for the invitation. It's been really lovely so far of the conversation. People I knew from different stages of life. So the topic today is, that of transient AGN distance. There's one relatively new to me, or like, this has been like 3 or 4 years up to the point before that. AGN disks were simply, gaseous elements that were feeding the luminosity that we see in AGN. That's all that I knew about that. But I've started to appreciate how they're actually objects in them, and this has led to a number of different, subset of research that I'll describe today, which, being the fact that they cover a number of different topics, has also been in collaboration with several people who have lent their expertise in several of the areas I will describe. So first of all, just making sure just a reminder, we're all on the same page. What is an AGN in a nutshell? So there are sustained cosmic sources powered by the release of gravitational energy via accretion on the supermassive black hole. So it's basically an accretion disk. But there's some elements, so I will just highlight the key topics that are will be of interest for later. So density in the disks are on the order 10 to the 5 to even 10 to the 15 in some regions, higher than typical galactic environments. So this is a very important fact that, as we'll see, will play an important role later. Lifetime, 10 to the 6, 10 to the 8 years, roughly. And they occupy the centers of, between 1 to 10% of galaxies. So this is, again, AGN interdisks in a nutshell. Now, coming to the actual topic. So the question is how, where is this idea of explosive events in AGN disks? So where is this coming from? And I feel like already in the literature, there were elements, for papers that then I went back to that, that suggested that this could be a possibility, but in a way, what it seemed to me, was like a trigger to basically the field that kind of exploded in a few years. It came with one very special gravitational wave events. This was one you probably remember, at least many of you will remember. It was one which was a very massive one, with the two black holes had 65 and 85 solar masses. And especially the 65 is borderline, 85 is somewhere that Mathieu will say is very uncomfortable for standard stellar evolution, because again, Mathieu and all the people who know these things very well will tell you that there is a gap above of in stellar black holes, which results from paired instability supernova. So there is a certain point where stars grow, but then they cannot be too big because their core will not be able to support them. And then that creates basically a gap in the black hole's remnant that can be produced. And that's believed to be around 65 with, more, give it or take it, with some playing around in nuclear reactions. So 85 was, very, was very away of it. I don't know, I cannot touch something like that.
There.
Oh, here.
I don't know who that is.
I would say decline.
Yeah.
I touch, is it touch or?
Should be a mouse.
I will keep talking.
Sorry about that.
No, it's not about. Thank you so much So why then AGN disks? Why the interest in AGN disks start in relation to this event is because in AGN disk there is one situation that if you have some black holes to start with, because of you're in 2 dimension, so interaction are much more likely. And therefore, black holes can very easily grow via mergers. So mergers are, very thank you. Mergers can happen with high frequency. So the idea there is that, okay, this 85 solar mass black hole did not have to be one that started 85, could have been, 2 other combination of 45 and 40 that made, up a merger or some going into gravitational waves, but just the idea is that you can have normal black holes, which have then merged as a result of previous generation. So all of this made, all of a sudden created the realization, in people that way. So we can actually have transit events, in this case is gravitational waves, from AGN disks. So it was basically in 2020 when these papers were out. From that point, a lot more interest in this area went. So why is this? It's well, it is.
Yeah, sorry, I was trying to do that.
It's okay. So then the first question that we have is like, okay, so we're talking about 2nd generation black holes, but first of all, where these primary black holes come from in an AGN disk. And here it is. So we go back to actually to literature, as you see, was actually much older. So in a way, the elements for transit in AGN disk were already there, except that they weren't really thought out in relation to transit up to recently. So there are stars in AGN disk, and this is the main key elements. How this is stars in a nutshell, where they're coming from. There are 2 main mechanisms by which stars can be found in AGN disks. So the first is in situ formation. The outer parts of AGN disks are known to be subject to gravitational instability. So these clumps collapse. So stars are very prone to forming just naturally in the outer parts of AGN disks. And there have been, these are just a subset of many papers discussing the in situ formation. But then the other, which is actually even more dominant in terms of numbers, is stellar sculpture. So we know that we know of nuclear star clusters. They're they're very common in galaxies. There is a dependence on galaxy type and supermassive black hole size, etc. But however, they contain, like 10 to the 4, 10 to the 5 for typical galaxies when they're their number of stars. Now, assuming you have a nuclear star cluster, so all your stars are very spherical with their orbits, but then a disk is formed. So you have an AGN disk. What happens is that the stars, as they circulate, as they go into their orbits, at every passage through the disk, they will lose energy, angular momentum, and eventually these stars will become disk stars. So there is quite a significant fraction of stars that get trapped by the disk. So that's the other way by which disks get the stars. And now, if we have stars, then there will be remnant to the stars, and transients associated with them. So that's the motivation and the reason for which transients are actually at least associated with stars are. So starting from again this as you see, there's a number of papers, all very recent. So how the field. So I'm going also a little bit overview how this AGN transients in AGN disks evolved. So it evolved in 2, let's say, general area. One is associated with phenomena that we already knew in galaxies, normal Normal transients, we already studied, loved, and these are examples. For example, gamma burst. We knew them, and they are very well characterized in standard environment. But then the question is like, okay, if we have stars and mergers, as we'll see later, we can also, we are expecting them also in AGN disk. So one question is, if we have, the same phenomena in an AGN disk, how is that going to differ, in their properties? So as you see here, together with the gamma burst, some of which I also, was part of my own work, but people discuss supernova, so things that we obviously know very well in standard environments, tidal disruption events, also known in a non-AGN context. They started to become also of interest in AGN disks. And then so this is again all phenomenology that we know in other contexts, but in AGN disks. But then there's other phenomena that are instead new to AGN disks. And examples, for example, here, that's something I will discuss. Actually, now I go with the things I will be focused on. For example, accretion-induced collapse of neutron stars. So these are phenomena that have been studied theoretically, but then when you are in an AGN disk, it provides a natural astrophysical environment for a phenomena that's theoretically possible to actually be astrophysically possible. So that's the general idea, and so my talk will be partly basically discussing some of the what I highlighted here. It's a subset of the lots of work that has been done in this area. So some of stars, so we know very well. They're very well studied in galactic environments. So how that changes in AGN disk and longer short gamma burst, and this is all the part of all the stuff we say in a new environment, and then some of like new. It's not really new physics, but it's a more astrophysical and new physics. So we start with the evolution of stars in AGN disk. It's also Matthias worked on that. So how does it different? So let me start again, since I'll be talking, I'll be covering different topics. I will be mostly like discussing the highlights, so what are the key elements of that, and then details, we can ask later. But I feel like it's missing one. It's slightly, but I will just say it's one word missing. It's okay. In the bottom somehow it's showing in a weird way. So there are two key elements on. It's not crucial. I don't tend to write it till the very bottom when you teach. You should write it at the last of the blackboard. Thank you. That's perfect. Thanks so much. So that's so there are two main elements from which are key in difference from evolution in a standard galactic environment versus AGN disk. So the AGN disk is very dense, and that leads to one key difference. That is, the star can accrete a considerable amount of mass during their life. Keep in mind that normally, like a star which is not in a binary, and as Kathleen knows very well, if the star in a binary, then there is exchange of mass, and that's one consideration. But if the star is not in a binary, then it basically they will like a vacuum. So the environment, it's basically having no effects on the star. So that's one element. In an AGN disk, the density is so high that a massive object like a star will actually be accreting effectively. And then there is the second element, is not only accreting, but it's a disk. A disk, to zeroth order gases in a capillary motion. As you know, capillary motion will have higher velocity as it's differential, like the velocity. So inner parts will be faster than outer parts. So if you have an accretion radius, which is a certain size, so if the star is accreting, one side with a gas with a certain angular momentum, which is transferred to the star more than the other. So the star is basically receiving, so it's in the reference frame of the star is feeling a torque, because gas from one side, it's it's accreting, but it's moving faster than gas on the other side of the star. These are stars that grow a lot. So basically, there is a torque on the star. So what is influenced is not only the amount of mass in the star because it grows, but also the amount of rotation. So the evolution of the star is changed, and this is so this leads to an interesting phenomenology, some of which was worked out by Matteo Cantiello and collaborators. Some stars go into immortal state, which we'll discuss here. Matteo also knows a lot about that because they go into a state of equilibrium where they burn at the same rate as which they they evolve. So but from my point of view, the ones that are in some areas of this where things are immortal are less interesting because they live forever, and then or as long as the AGN disk is alive, and then they don't go off as transient, so there is no transient associated with them. So I'm interested in the ones that actually are still able to evolve. So we studied that with Matteo, Adam, Germin using MESA, which is the standard of for star evolution. And basically, just in a nutshell, so there are, a star or normal, or like a star in a standard galactic environment will only reduce mass through winds. But here you have a star which is also gaining mass and it's gaining angular momentum. So there is a different evolution that we studied. So what happens by the end of the day of the life of this star, which was the question when I started to work with with Matteo and Adam, that was of interest to me, which is, are the stars potential candidates for gamma ray burst? Because I am interested in transit. So what is the, let me just review, what is the one element that you look at when you wonder if a star, which massive star go off as a supernova, also gives rise to a GRB? So to zeroth order, just in simple terms, but it's the main element that we know of, that we believe differentiates, or more than differentiates, adds a gamma ray burst to a supernova of a star. It's its rotation. So normally, a star, will go off a supernova once its core becomes, either a neutron star or black hole, cannot burn anymore. But then, if it is fast rotating, when the core collapses, and the amount of material which is surrounding the newly formed black hole has enough angular momentum to circularize, then it's falling back, but it's also forming an accretion disk. And nature has this very interesting way that at those scales, when you have a rapidly accreting black hole, it's driving a jet under many circumstances. So this is, like science that has been discussed for long GRBs for the longest time in standard galactic environment. So the idea of what makes a GRB in addition to a supernova is the fact that the star is highly rotating. So we asked this question for these stars now in the AGN disk, since they have this very special evolution and they're subject to a torque. And in a nutshell, so you see the answer here. So you look at quantitatively to answer this question is the specific angular momentum in the burning layers of material just outside of the core to see if they have enough angular momentum to circularize, to form a disk. This is the specific angular momentum for Schwarzschild and the carbuncle. So that's, you need to have, you need to have more angular momentum in order to be able to be in an orbit around the black hole. So the answer is, so this is a J, specific angular momentum. As you see, for these stars, what happens, is basically typically is that they have enough angular momentum to circularize, and therefore the answer to the question is that stars in AGN disks routinely make long GRBs. The time scales are here, so the free fall time, which gives a zeroth order estimate of the duration of the burst from as material falls back and replenish the disk. So we have established already one first fact, and that is that we do expect long GRBs routinely in AGN disk. So with a higher efficiency than the galactic environment. The galactic environment, this rotation is typically, it's 1% or so of stars. In an AGN disk, if the star doesn't become immortal, it's basically common. So we would have a very high efficiency. So first thing,
Can I ask a quick question? So how are you actually calculating the angular momentum deposition rate? I mean, this is like a big problem in protoplanetary disk study of determining like the size of a circumplanetary disk. It seems like similar physics, but I understand you put this J dot into MESA. I guess.
That's right. So this is basically, it's basically in here. So there is an extra additional angular momentum.
But how did you determine what that J is?
Right. So this J is calculated as to zero order is omega times r squared, the accretion radius. So it's
what sets the accretion radius?
So the accretion radius, so it will be the Bondi radius, except in AGN disk is a bit modified because if there is a supermassive black hole, so if the Hill radius is the minimum between the Hill radius and so there's like, but to zero order is a Bondi.
And it's you just assume like ballistic trajectories from what's ever smaller, the Hill or the Bondi.
So that's right. So this is well in MESA, this is like I think Matteo will know much more in detail, but it's like a boundary condition. It's posted the star.
Right, but to get the J that you put into MESA,
right,
it's ballistic infall from
the accretion radius. Yeah, that's right. Yeah.
Thanks.
Of course. So it's so that's for longevity. So now we are going. So that was that. So then the next question is, so we have, as I said, we have black holes, so we have stars, so we'll have some neutron stars. So the next question is how neutron stars will evolve in an AGN disk, and are there differences compared to the? Yes,
I can go back to the previous.
Yes, of course. I'm yes.
No, I mean, I have a different question. I mean, aren't there some inherent assumptions about the black hole that's forming, essentially spinning at a very high rate? Like, isn't there, because like after LIGO started finding all these like 50 solar mass black holes, 30 solar mass black holes, people started talking about, okay, what is the mechanism that we transport angular momentum, in the inner core of the star?
Yeah.
And so there's all these uncertainties. And so I'm curious, how do we know? Because like in order to be able to launch a very strong jet, you need to have a rapidly rotating black hole. But how do we know in this scenario that it's common? If we're going to make the statement that this is what AGNs, what these stars are going to be looking at AGNs, that we're going to have gamma ray bursts associated with supernovae or something like that.
Yeah, so I guess here the thing is like we go a lot by analogy with the physics of long GRBs in standard in standard environments. So for standard GRBs, the idea is that the idea is like, well, first of all, we have ideas about the speed of the core, and this again, Matteo will know these things better. So given some assumption, because it's a lot depends on the assumption you make on the angular transport within the star.
Right.
So within a certain set of assumptions, so if you will have a certain, the central black hole will have a certain angular momentum which can be predicted. So in that sense, it's it's not as the AGN component here with respect to the standard physics come from the fact that it's basically keeping the star rotating more efficiently. So that's basically the difference. The rest is like same issues that we have.
To make that assumption, are you making some assumption that about the star being a uniform rotator? Because like you have matter accreting from the exterior, from the AGN disk, but like we're talking about vast timescales here, of course. So how do you know how that angular momentum is being transported down to the core?
Yeah, so there's again.
Maybe I can help. You use
like,
the standard Spitzer dynamics, so the same assumptions that you make for normal non-AGN progenitors, with all the uncertainties that you are aware of and integrate.
Yeah, it's a big uncertainty. So it's always like if you make a certain assumption for angular transport, but it's again the AGN part only comes in the extra boundary condition, but then we are down to the same uncertainty. People work with MESA are very well aware. So it's Now that is for long GRBs. Now now let's look at just the normal neutron stars. So here it's an all different range of physics. And in particular, so codes that I've been using here have been developed by Hiromichi Tagawa. So let me just give the basics. So in a disk, one populates it with the compact objects, stars, and the neutron stars, which are what I particularly interested in. And then these codes, they follow binary formation, binary disruption with processes, the effect of gas in shrinking binary, triple scattering, which can break binaries, gravitational waves, which shrink binaries, and so forth. So it's all it's a sort of statistical type of code. So there is no hydro here, but there are prescriptions based on hydro. And so by the end of the day, with running these codes, which again there's been many papers written by, let's say here, by this group of people developing them. But what I was interested for me was the output. So what is in particular two aspects, one of which I will discuss later, but it comes out of the code. So as a neutron star is followed, it is location within the disk. Its mass is being followed as it grows due to accretion, and also how neutron star form binaries. They're being disrupted, but all the ones that survive by the end of the day. So I was particularly interested in these two aspects. So I started collaborating with Hiromichi and borrowed this code for this type of analysis. So I'm just going to the end, but having given an idea what is what are the inputs here. So with this population that again starts tracking by some that are in situ, some that are being trapped, are being captured. So all it's being put together. Then one can study, so they follow, and then statistically one can, the information that we get is where, how many there are as a function of the radius, as a function of the disk, radius, radial position, how many there are as a function of scale height, and as they form during the typical AGN lifetime. So these are neutron star mergers, and as you see here, this is just a dash line typical AGN lifetime, just as a reference. So there will be a number which is several hundred to the absolute normalization is something I will never explicitly use as a rate, because those are uncertain, because it depends how big is your nuclear star cluster. So there are uncertainty connected to that. This was like an average nuclear star cluster. So ends up with something like on the order of a few hundred of neutron star merger during the AGN lifetime. So what does that mean? We know by now, at least from one event, only one, but from one, that short GRBs are associated with neutron star, binary neutron star mergers. So we, given these results and the fact that we do expect binary neutron star merger in AGN disk, the corollary is that short GRBs from binary neutron star mergers are also going to be in AGN disks. So from this first part of the talk, the bottom line, so in a nutshell, is that we have both long and short gamma burst. Now it's the top, that is a little, but it's okay. Both long and short gamma burst are expected in the disk of AGNs. So that is first element. Now I'll move on to the next question. So as I was saying, part of this research has been into if we have transient in AGN disks, how will they differ? So I've hopefully convinced you that we do expect some of both long and short. Now the question is, what are the chances of a transient? And we'll particularly focus on GRBs because they are the ones that we know very well. We have studied very well. We know the physics in the or at least to zero order, we know the physics in a standard galactic environment. So how, what are the chances to see will it be modified compared to a standard galactic environment? So this will be the next question now after we establish that we do expect these events. So GRB explosion in AGN disks. So I'm moving on through from one pretty picture to just a schematic view of what we have here. We have a GRB which we'll put in the center, in the center of the disk, because that's where objects will tend to settle. There will be an observer looking some line of sight. And then here, so I'm putting this, which are typical models, just because it will help to understand a little bit later some of the results. So AGN disks have been studied in detail with the Shakura-Sunyaev disk, first, the first and still like a very good zeroth order model. H of A is the it's the scale height of the disk. Shakura-Sunyaev is about 0.1 roughly. However, there have been models of increasing complexity, and these are two that have been becoming very popular in AGN disks. So also there's been a public code that produces AGN disk model, based on this. So this is a Sirkon Goodman, and this is Thomson, Patart, and Murray. So those symbols are. But I'm showing here just because later some plots will look a little bit nonlinear, like with just showing that it's the scale of a height is not a simple linear. It varies a lot depending on assumptions. So a lot of what I say is still quantitatively, obviously we cannot be exact because it's still the structure of the disk is not it depends on assumptions and so forth. But just to give an order of magnitude, these are the densities like super high, as you can see, but again, model dependent. So just as a reference for later in these two models that I will be using. So that is why I'm showing it now. So we want to see how a gamma ray burst is now modified if it is in an AGN disk. So for that, let me just review the basic physics of a gamma ray burst in standard interstellar medium, so that we can see what is that changes there. So this is again zeroth order phenomenology, how we we believe it to in the standard model called the fireball model. So there is an explosion, same so longer short GRBs here, so central engine. So there's at that point, then the later phenomenology is very similar, which is why they look very similar, even though the progenitor is completely different nature. So a jet is released. There will be, first of all, photospheric radius is where it becomes optically thin. So radiation from that point on, we can see it. Then there is a radius, effective distance, basically. It's called the internal shock radius. This is where some of the energy of shells of different Lorentz factor that we believe are being driven by the internal source. They start, they collide. Some of their bulk energy is dissipated and give it rise to gamma rays. And this is the gamma ray burst part of the emission. Then as this, these various shells collide with one another, eventually you have just one big shell that at some point starts accumulating enough material comparable to its rest mass. And that's when the external shock what we call external shock start forming. And from that point on, we have just a continual radiation that goes all the way from early gamma rays, then X-rays, optical radio. So it's the whole spans the whole electromagnetic spectrum, and at some point it becomes non-relativistic and it dissipates all its energy. So that's basically gamma ray burst in a nutshell. So the question that we then asked, and there was work with Davide Azzati primarily, what happens if a gamma ray burst now occurs in an AGN disk, so much denser? And something that it's actually, it's interesting here is that people have never asked this question before, if something, in a very high density, because, we knew GRBs in, just in galactic environment, the densities are, are low. So nobody really, above 10 to the 5, which is dense, dense molecular clouds. Other than that, nobody really cares. So why do you, work on a problem if there is no application? But then all of a sudden it's like, oh, there is like AGN disk, so let's work on the problem. And then we had some surprises as we were studying, how the event will look like. And here, again, I will describe just the basic physics of the changes. So what we realized is that, as I said, the external shock is being formed when the fireball is accumulated enough mass comparable to its own rest mass. If you're in a very super dense medium, that happens very quickly. So something very, peculiar was happening, that basically we are finding formally that the external shock was formed before the internal shock. So a reversal situation which happens above these densities with exact value depending on the Lorentz factor, so maybe slightly different depending on long or short GRBs in the energy, but roughly around this value. So what did that have as implication now for the gamma reverse phenomenology? So it had several, several bits of information of implication. So all these pulses that normally are the results of shells colliding, you don't have anymore because you have a new shell, but it's already hitting against an external shock, and then a reverse shock is formed. So instead of seeing this, very spiky behavior that we have in GRBs, you basically have a convolution because one, comes back, and you have a reverse shock, and then a new one goes. So it's basically they become spread out, and they become a convolution of all of them. So what we noticed was something very particular. That if we start, for example, with the short GRB, here is an example with an energy duration of a second. Because of this spread, because of this, them hitting a reverse shock and returning, the burst was actually appearing longer. So it was appearing. So this was an example that we had, like a theory in a theory paper, was becoming about 3 seconds. Also the light curve was much smoother, didn't have, obviously all these spikes. And it also had another fact in the spectral evolution, which is what we call R to soft spectral evolution. So what does it mean? It means that the peak of so gamma reversed have a bound spectrum. There is a peak energy. It's declining with time. So normally in gamma reversed, for the greatest majority, the luminosity and the peak frequency track one another. So there's a tracking behavior. On the other end, we found that for these spectral GRBs, there is not it's just basically a decline instead of correlating with the luminosity. So they were all strange facts that were coming out of the theoretical work. Now one of these fun facts that sometimes happens. So as we were working this paper, we had not was not out yet. David, the first author, was at a conference where he met an observer, Andrew Levin, who said, look, we have here this very bizarre event. It happens within 100 parsec of a nuclear. So it's it's a nuclear one. It's a 0.2 redshift. It's long, but there is no supernova. So it's very bizarre because it's it should more be we should see a supernova, but we don't have redshift, but it's long. And it has also the spectral evolution is kind of interesting because it's not really tracking, but there is a hard to soft spectral evolution. And we're like, wait a second, we are actually just, so it was one of these nice things that happens sometimes. And he basically gave us the data. Then we took a while because we had to wait for them. The paper was in Nature, so they were holding on to the, we had to wait for them to first publish, but we started the interpretation. And basically what we saw, we took just a very standard canonical GRB and, and basically doing a fitting to see how, which density would give. So these are the data, and whether we could reproduce it. And basically we can reproduce. So it is possible that we may already, so I suggest we may already have a candidate actually for a transient in a disk, so in an AGN disk. So the one thing I should say is that because they have limits on the X-ray, so they don't have a detection of an AGN, but so it would be a low luminosity AGN, which there is a number. So the limits were a few times 10 to I think 43 or something. So it would be a low luminosity. So at the so it's undetected. So that's the one thing. It would be a lower one, but it's actually the fact that it's so well seen. We can only, as we'll see from what I say later, we could only see one very well detected only if it's a low luminosity one, only if it's a small one, otherwise they will be diffused, as we'll see later. So basically, yeah, bottom line is that we may already have one, and also actually now I bring back these curves that I was showing before, just now they make more sense, because actually when one step further, so these are coming from the fit, so it just the spectra fit to the burst. You know, if we start with the standard, you know, short GRB properties, what density do we expect? So this were, you know, density, they were somewhere around here in terms of, you know, if you take these models from, you know, from the literature. And then we'll go back to the, you know, to the paper that actually was before everything else, but that I described before in terms of the work. It's like where in a disk you would mostly likely have mergers, and they're mostly concentrated into regions because things migrate. There's a number of reasons for which time scale that that basically have objects concentrated, you know, specific. So it's maybe a coincidence or maybe not, but basically the region where they would be concentrated. So here, this density here corresponds to one where we predict, you know, from completely independent work that you may expect an enhancement in mergers. So here we go. So this you know, transient AGN disk is something that the field may already restart not only with theory but also with an actual observations. And we believe we have a very strong candidate for that. So now so more generally, so this again, as I said, it was a case that, you know, appeared, you know, was influenced by the environment, so very high density in the way, you know, in the intrinsic properties, let's say, were affected. But then we have in an AGN disk, there's then one extra layer complication that you have your source, but then it's propagating. So in a very dense environment, so that can further modify the transient. And this is so something which also so very important that we looked at. So let me first again just describe the physics of it. You know, what are the main elements because it, you know, and then we go to the colors here. So let's take a GRBs that it's in the plane of a disk. So there is a jet, and the disk will have a certain scale height, which is very variable, which is why I showed that, you know, before. It's you know, it varies a lot with the radial distance. So you have your scale height, and you have, so there will be a certain photosphere for the disk. So there is optically thick up to a certain point, and then above it you will be optically thin. Now, so you have your jet. Let's say you can you can be in region of the disk where from the beginning you're optically thin, because there are regions of the disk you're fully optically thin, and then it's normal. Then you have a normal GRB. The fact that it's in an AGN disk, it affects the intrinsic emission as we saw before, but it doesn't affect anymore as it goes out. So it's not diffused. It's you know, it can get out normally. So that's one situation, and actually here it's the blue region in this part. Again, there is no linearity because of the scale height and density are not very linear with the disk. So those are the meaning of the blue. Now let's go to another situation. So we have our GRB here. So this is the jet, and the jet is, you know, is emitting it from the surface, and it's also propagating, you know, coming out. So imagine you have a situation where at the beginning you are below the disk photosphere, so it's optically thick. But then as the jet, you know, this is the disk photosphere. At some point, you know, the jet is advancing and it's emitting. At some point, it emerges from the photosphere. So from that point on, the radiation will be optically thin, will be basically undiffused. So those are the orange area, which are regions where, so that's, you know, diffused early emission, but then later it's unaffected, the afterglow, because it's emerged. And then there are other regions in the disk where, you know, basically the full evolution is diffused. Basically, it's optically thick throughout, and those transient, which I'll describe a little bit more, then, you know, we won't be visible at all. They're, you know, just emerging on the diffusive time scale, which is this number here. So year, month, that is what represented So these are basically, plots where every point in the disk we calculated, we started with the jet, and then, numerical is basically looking all this radii. That's basically the meaning of it. Then a student, former student of mine, also calculated a little bit more in detail. So I did Monte Carlo to see, how would these curves, light curves will look like. So it's basically just a more quantitative way to express this. So if it's so situation, for example, so here the blue is just appearing, normal. Like the orange here, it would it's early time. These are different angles, so let's just look at the angle. So at early time, this is the intrinsic and this is the emerging. As you see, there's a difference because it's diffused, so it's suppressed, but then at later time it start becoming comparable. So they become basically the emerging. It's the same as intrinsic. On the other hand, if you are in the green part here, it's all diffused, and it will appear on a diffusivity time scale, which is very long and very dim. So we wouldn't be seeing much at all. So there is a
is the angle with the angle is the axis of the GRB with respect to the disk?
So the angle is the viewing angle. So here it's so these are figure for simplicity. So the jet is going perpendicular to the disk, and this is the viewing angle
of the AGN. Okay,
right. With respect to the jet axis, which also here they made to be coincident. So it's like the viewing angle with respect, because the emission of a GRB is also very angle dependent.
Right.
So at larger angles, it's just.
But what about the background AGN disk?
Oh, so here there's no background AGN disk. So then it would emerge because it depends on will depend on the AGN disk. So it's so here most of this would be below the background of the luminosity of AGN. So it depends. You have to look band by band, where the AGN disk, what is the luminosity and that. So yeah, so
for does the viewing angle of the AGN disk also matter?
The viewing angle of the AGN disk, well, it will matter for the luminosity of the AGN,
but not for the propagation of the jet through the scale of height. I guess I'm imagining if you're not looking down.
Yeah. So we did also, as part of the paper, we also look at side angles, but I didn't want to because it becomes so much. So this is the two angles are basically the same because it's made to be perfect, which actually I think had. Here, as a matter of fact, I think I had this question before, so I had a plus. So this is like this is the angle, right? At the viewing angle, it was here on the represented. And okay, so I have 10 more minutes. So I guess just to wrap up. So this first part, which is majority of the talk, was on new it was all the phenomenology, stars, long and short GRBs that we knew about in AGN disks and how they will be different, and the fact that we'll likely have some. And now go to the other part where I said AGN disks provide interesting environment for new phenomena that in normal environments are not likely to happen. And this was one that, again, as I started to work on AGN disk, occurred to me, since there are neutron stars and I saw the accretion rates are huge. So I was like, okay, then maybe what can happen is that occasionally you have the accretion induced collapse of a neutron star to a black hole. So let's motivate it first a bit more, just give us some background for things that I'm sure you already know, but just the key elements is that a neutron star can only, depending on the equation state, so the exact value will depend on the equation state, but can only be sustained up to a certain mass. If there is rotation, that can be higher for a certain period of time, but otherwise, the star above a certain mass, there is for a given equation state there is a maximum, and for a range of equation state above 3 is basically it's always going to be a black hole. So that is first fact of nature. Then there is just looking at the disk, the accretion rates. So again, take it 0 to order, just order of magnitude that we're doing here. So accretion rates, so this is a thick Bondi. So these are there's a huge range of densities. So if you take a Bondi accretion, these are typical accretion rates that you can achieve, and just as a reference for one solar mass, the accretion rates Eddington is 10 to the so this can be very 10 to the 18, so they can be very they can reach Eddington very easily in most regions of the AGN disk, assuming Eddington is the maximum, or a few times Eddington, but for neutron star is more than that. But even you take it just at the Eddington limit, in 30 mega years you can grow. Let's say you start with a star with a normal mass, you can grow it above a value which neutron star, for some equation state will turn into black holes. So that was an interesting fact that just occurred to me with doing 0th order magnitude estimate on the time scales and accretion rates. So as I was working with again with Hiromichi, and this was part of the same same paper, so we were looking at neutron star mergers, but also we were looking tracking also as neutron stars were growing. So we basically, just as the neutron stars are moving in the disk, as they were simulated, so you can ask the question, how many will undergo IC, and you see, so there's the answer here. So again, it's as a function of where they are, scale height as before, the x-axis that disappeared from here. It's the same as the other, and it's a function of the disk lifetime. So they're, in terms of numbers, they're somewhat comparable to the number of neutron star mergers. So it's a few hundred per disk are supposed to undergo accretion-induced collapse. So with that in mind, then I started to look in the literature of what does that imply. So I never it was not a topic except for one work which I thought too much, but there are people, including you have here Vasily, who have been working on the phenomena associated with the collapse of a neutron star into a black hole. So just again the very basic physics, because there have been a number of papers that then I discovered that were in the literature on that. So as a neutron star, especially magnetized neutron stars, as the neutron stars collapse into the black hole, because the black holes have no hair, so they have to get rid of the magnetic fields. So there's lots of reconnection that goes on as the collapse happens, and people have simulated this phenomenon and predicted what happens with that. So the prediction, which is again in a nutshell what's of interest here, is that there is energy which is radiated away. It's basically electromagnetic energy coming from essentially reconnection. And as a matter of fact, it has this type of phenomenon early on had even been suggested as a possibility for one explanation of fast radio burst. So it was one of the early models that was suggested. So basically, there is this phenomenon that well, let me actually continue with one more. So this is independent now. It taps also in vacuum. So the fact that it's a phenomenon of just a neutron star collapsing into a black hole. Now, why it's of relevance to AGN disk here is because a neutron star on its own in a medium is not going to accrete as much mass to collapse into a black hole. It will never do it in the age of the universe. And even Kathleen, maybe you can correct me, even in a standard evolution neutron star, with a banner, like the mass that accretes on the neutron star slowly during time, it's not going to turn the neutron star into a black hole. So all of a sudden, AGN disks became the environment where a phenomenon which would be studied theoretical can actually be realized in nature. And then also an extra, just one extra addition, if the accreting gas has some angular momentum, then during the collapse there is one extra addition, that as the neutron star collapse, a mini disk is formed. This is something that we simulated with the former postdoc of mine faculty with GRBs simulation, the collapse under the presence of matter. We found that there is basically, it's followed by a rapid accretion of of material, so a mini disk, which is potentially, as the neutron star turn into a black hole, has similar features to what we have in GRBs. So it may possibly even drive a transient. So here this would be a very funny one if it were to happen, because you have the neutron star collapse into the black hole, and that's from the magnetosphere. You may have that FRB like, let's say, type of transient. The simulation before have shown to be the case. But then if there is some matter surrounding the newly formed black hole, you might trigger some type of jet and a GRB-like emission, like short GRB-like emission, but without associated gravitational wave emission. It's not a merger, but it's just a single neutron star collapsing. So that is a phenomenon.
A rotating neutron star?
So this was I think this was a rotating neutron star, but I will have to double check on that. Yes, because I mean for forming for driving a jet, a rotating black hole is kind of a necessary condition.
So why do you not get a gravitational wave emission then?
Oh, well, I mean, no, you're correct. Like I shouldn't say no associated GV emission from like the binary neutron star merger. So it would be a short, possibly.
You get a gravitational
yeah,
wave
but
from
you
the
would have it
collapse.
from the. It would be so. Yeah, I should make it more precise. I meant to say no gravitational wave emission. Suggesting a binary neutron star merger. So you may have something that may look like a short GRBs, but without the related.
The in spiral.
Without this spiral, yeah, GV is spiral, so that's the missing thing. Right, thank you. But it would be the other associated with, that would require to be very close to us, which we don't have an AGN in our center of galaxy, but it's a bit of that's why I guess I use that as default. But yeah, so this may be a new phenomenon that we're not seeing, but we should look up for it. And I'm basically at the end of the time and at the end of my talk, that likely go at the same time. So just a quick reminder what I said. So I hope I convinced you that the disks of active galactic AGN disks are very interesting places where, well, there's compact stars, compact objects, and where we have, well, stars, so details that we discussed where stars evolved on different evolutionary paths than in isolation. Compact objects can undergo substantial growth, yielding new phenomenology. In particular, I discussed the IC, but then also the disk itself can affect the radiation from the transient. So GRB short, short GRB can turn into long GRB, and possibly we already have a candidate which was a peculiar event. And then some of this, like diffuse can potentially be contributed factors towards AGN variability. So actually some observers have got interested in looking, and there's a lot of unexplained AGN variability, as my understanding. So they've become interested in some of this may actually be associated with transient where we're missing the early emission, but we may see it later in other wavelength, and that's.
And we're kind of almost at the time. Is there any pressing question you want to ask? Even online, if you want to type it or unmute yourself.
So when you mentioned the GRB 1910-19A, which appeared as a long GRB but was better fit with a short GRB, did they not say some kilonova associated with it, or was it too far?
Right, there is no that at least to my at least up to the I haven't followed that afterwards, but there is at least up to the moment there was no sign of any.
You said the redshift was 0.28 or something.
0.2,
That's 1500 megaparsecs. That's too far.
Okay. So it should So for supernova they would have seen it.
Right.
If there was
But
there was
kilonova,
so there was right.
far.
So there was not.
A kind of related question directly, which is like all of these things, these transients that you have embedded in the AGN for this talk are considered our process sources.
Yeah.
At least the binary neutron star
stars,
mergers,
right.
that there is no doubt anymore, but also collapsers might be one source. So should we expect AGN to get enriched by our process, and can we test this with
So
GWST spectrum? for
yeah, it's
example?
an excellent question. I think there's already their paper. There was one, I think Barry McCurry. They're looking, basically they looked at the enrichment. So it's a follow up on that.
Or let's go to deep one first.
Quick question about the first part of your talk when using MESA to model the star in the AGN disk. Given it's probably quite an asymmetric problem in terms of the shear motion of the AGN disk, how good of an assumption is 1D?
Yeah, well, it's again, this is, I will answer, but I'm sure I can. So, MESA, as you may know, it's like, it's 2D, it's a 1D with, it's another real one. So it is very approximated. It's not a real 3D, because, for rotation or 2D, you would need it. But there, rotation is put a little bit as an extra degree, and you can be more quantified,
You can use coordinates to reduce your problem back to 1D if you assume that the horizontal angular momentum transport is infinitely fast, which is an assumption. And then if you want to evolve the stars from main sequence to core collapse, no matter how bad it is, that's what we'll have for the rest of our lives.
That's a very good answer.
Yes. So I have a question about the compact objects that are embedded like within the AGN disk. You talked about different regions, like optic regions. Is there like a preference of where the compact object would be distributed across the disk?
Yeah, absolutely. So there was, I know because I've covered a lot of things, so I may have gone through, fast. So in here I didn't even have coordinates. So yeah, for both. So with this, with this codes by Hiromichi that has it with the, and now with MC factor, actually it's an evolution of that, as you know already talked this morning. So yeah, we can predict where they are. So this is basically in radii. So it's log of in units RG, which I don't have it.
So are you usually in regions that are more optically thick or optically thin?
So right, so so the outer part, some of the outer parts here, they're actually optically thin, but also it depends. So it varies with between the Zircon, Goodman, and the other, the TQM. So they make different predictions from the. So the answer, it's not unique because it's model dependent on. Depending on what they are, but yeah, they tend to be more in outer parts, and then some in inner parts for the neutron star mergers where they migrate, and so they tend to be. There is this gap, the migration traps that tend to form, and neutron star mergers tend to be more there, which are more in inner parts.
One very last question.
Thanks a lot. A lot of fascinating possibilities. Can you give us a feeling for whether this is an exotic phenomenon or something that is very common? So if I take a class of objects like all gamma ray bursts or all gravitational wave events, what's the percentage of these that could be happening in an AGN?
Yeah, so it's an excellent question. As I said at the beginning, I'm avoiding making statement of absolute rates because they're very they're very uncertain. So for example, there's the AGN channel so forget about like now GRBs, but the two things are connected because they all connect how many we have. So there is the gravitational wave events you mentioned. So how many they come from AGN disks. And there is, as Matteo sure is when he was in CCA. So there is, between like a small fraction of percent to some groups that get varying the, parameters still within ranges that are reasonable, but you just, push every parameter to their, most favorable one, which could be even 90% or that. And then obviously, if those, gravitational wave events are larger dominating, then, and if you have as many black holes, that means also implication for the stars that produce them. So there will be many more. So yeah, something I'm actually looking now, it's exactly like a line. So try to cross-correlate it to say, okay, if you have a certain number of gravitational events that come from AGN disk, what that has implication in terms of GRB events, because there is a same population, there is a population of stars, and if you have a certain number, which is the absolute numbers, is highly uncertain, but then if you predict that we have these gravitational events, 50%, say just a number, come from AGN disk, that will mean that a certain number of GRBs will have to be there. So I'm trying, thinking of the two things together. But, it's a very good point. Indeed.
We should just thank Rosalba.